viewer and follower. So I welcome you, sir. We are all honored to welcome you to have this presentation today.
Thank
Please
you.
join us, sir.
Okay. Shall I start?
Yes, sir. Yes, sir. You can start, sir.
Okay. I'm thankful to Yogi Vemanna University, Kadapa, for giving me this opportunity. And of course, my student, now teacher, and maybe knowing more than me, there are many people around who are well qualified, well aware of new technologies and what not. But still, I should congratulate on the theme which Dr. Mamta Kumari has given, advanced materials for energy and environmental application. So I think it should be known to everybody, and I'll just give a name before starting these things. Graphene is uh, one of the most wanted substance in this regime. So I'll start with one incident which happened with me in 2008. I was driving car. I was driving car from Indore to Bhopal, and speed was, of course, a little more than 80 kilometers. And suddenly it starts raining, and we found that the drops which were falling on the window or front glass, the drops were moving up, not moving down. Then immediately I recalled that observation has a crucial role in understanding things. Of course, if you reflect on it, then and discuss maybe more and more uh, knowledge we can gain. So, just I thought uh, my topic should be how observations followed by reflection and discussion leads to pragmatic. I am emphasizing on this word pragmatic innovation and research. So, uh, when we say observation or when we say experimentation, it's not only my view, but unless experiment is done, whether what parameters you are doing, taking, everything should be known to us. And unless we are serious, observations, everybody does it. But there is a word I am coining today is that power of experimentation and power of observation is so great that we can achieve anything which we feel we want. For example, when I say power of experimentation and power of observation, that I am leading this towards new materials, and then maybe I'll show something different also. Uh, Everybody knows that it was Newton, people say, that an apple fell on it. So I don't think before that nobody saw apple falling or a meteorite falling or even small leaf falling down on the earth. It is not new. Everybody knew it, But nobody, I'll say nobody, but um, maybe I should say carefully, most of the people did not see it or did not see properly, or I call now a scientific word, observe properly. When you observe very scientifically and with reflection, then things become different. It is not only apple falling, everything is falling on the earth. But why it is falling? Even our Nobel Prize winner, C.V. Raman, in his
In
childhood,
his childhood,
he saw why earth is some different color, why sky is blue, or why sea water, or when you see through some water, river water, why these things have different color. But I can say very well that it is not only C.V. Raman who noticed it, many must have noticed. Even the people like Rutherford, or you can say the other people, they also saw it, but they did not bother about it. So one should bother about observation.
Madam,
And anything to be
ah,
told to me? Is it audible? I think.
okay,
sir, it
okay,
is audible. Somebody else
Okay.
has come and didn't unmute, sir.
So
okay.
Yeah.
there may be sometimes a, a contrast, or you may say controversy. Who came first, observation or theory? But whatever observations, experimentations are done, they are the real objects, not theory. Theory is based on it. But there are cases where prediction is done on theoretical basis and the experimental is done quite later. If you recall, 1932, neutron was predicted, but it was discovered quite later. Similarly, is the case with the neutrino, and hence, uh, who is better, which part is not better, we need not go into that controversy. And but now I start giving some examples, and then how it leads to something better understanding, etc. So, shall I take the example of Brownian motion, Brownian moment? I think pollen grains were moving from one direction to other direction. They were not, if I say, at that time, animal with movement, live animals or live particles. So they themselves could not move. But still, when Brownian moment was observed, bigger particle which we can see, which we could notice, were moving haphazardly. So what is happening in between? If they are not colliding with each other, if they collide, no problem. We have several rules for that. Mathematics can come inside, and more illustration can be there. But if we say something must be happening, it is not only that pollen grain suddenly changed its direction. So what is that? So something was there. What is that something? Then kinetic theory of gases tell us why that something was so powerful that the energy was imparted to pollen grains. If this is the case, then there is one more thing, very, very common to everybody. and that is candlelight. In candlelight, we feel that outside part also is hot. Now, that is some kind of plasma. Something is there which is not visible to us. So, it is not necessary that whatever visible to us is the only thing which exists. No, it is not like that. We may not be able to see many things because we have limitations, and for that reason we say only Vibgyor, violet to red. But infrared was also there. Probably once a simple experiment I showed to our participants, because people say that when we cannot see before red, after wavelength increases more than the red region, then how we can claim that it is having heat? Then immediately I focused light on a prism and then showed it on a white paper. We could see the colors, and when red stopped, we could not see that. I put a simple thermometer outside the region of red, and still it was showing increase in temperature. It means infrared has uh, heat. We should say thermal energy, the better word. So these invisible things have something to say, and such things are there with sound also. We just make a simple statement that human ear can listen to frequencies, mechanical frequencies or vibrations, you can say, from 20 to 20 kilohertz, 20 hertz to 20 kilohertz. But I'm having some doubt. We have now our audio listening meters, and what I say is the lower limit is more, not 20. 20 is ideal. Say if I want to listen something, my limit may be something 30 like that. And higher limit is, for me, of course, was 12,000, not 20,000. So that part we should always remember. In the case of light also, we say 4,000 angstrom or 400 nanometer to 7,000 angstrom or 700 nanometer. But it is not same for all. And from species to species, it differs. What we are not able to listen, say if frequency is 10 or 5, some animals are there which can certainly notice that. There are some animals which can listen to, or at least feel the frequency which is far beyond 20 kilohertz. So I just recall a statement of uh, the biggest, or I think the most versatile teacher used to be said as Feynman. He used to say, if you are not seeing something, it does not mean that something is not happening. And then he gave the example of a fire. Fire in the jungle. If you see the fire, you say, yes, it is happening. But if you don't see, still the thing is happening there. So these things, I think, we need to know. Then one day I was reading one book on different aspects of physics. I saw that Levise, who gave the name oxygen, of course, he gave a method to prepare it, but before that also something oxygen like,
ఇంట్లో ఫిష్ తినొచ్చునండి నేను
something was there which was called phlogiston. So um, Levise was the person something around 1790, around that period. He had 4 or 5 friends, and all the scientists quite good at their at science information and evolving science. Of course, father of science, physics or father of science is known to be Galileo. We may come to him afterwards. But what I appreciate was with Lavoisier during 1790s, he used to call his friends, 4 5 friends, to his house in the evening to take tea. And during that tea hours, he he and his other friends used to discuss different topics related to science, and then something would of course come out, or it was not a futile discussion. Something always comes out when we discuss things, and discussion is always between two minimum. Discussion is not one sided, it is to be reciprocated. So when they were discussing, scientists were having some encouragement or something of that sort, that what can be done now. Let me talk about a few more observations other than what Newton said. But before that, what I started in the beginning saying something, just a few days ago, a research scholar asked me, "Hey, sir, this Bernoulli's theorem is or can be demonstrated?" I said, "Yes, 2 3 ways." I showed him immediately, and then I told him to sit in my car. I purposely put some flowers on the wipers and then started the car. As car took a speed of about 30 kilometers per hour, the flowers were moving up on the glass, front glass, and they moved up and of course then disappeared. Here I showed that the wind which that screen is uh, having impact on, that makes the flowers go. But in Bernoulli's theorem, what they say, same thing, that pressure is going down, so things go up. And for that reason, I'll tell two more things. which are there in YouTubes, and so many wrongs are also there. So I don't believe every experiment showed on YouTube to be true, because we say there are several places, 4 5 minimum, but two places are prominent. One is Leh, where our car moves up. We are not putting it on. It is just on neutral, off, engine is off, and at particular point, if you leave the car, that car will go uphill. Same thing is told about Tulsi Shyam near Deep. I personally visited that place and I asked people, did anybody come here to say this? They said, no, we never found it. But of course, they said some 7 8 years ago, a team had come and they were doing something on the road. And now that road is so bad that nothing can go up or even down, because that road will not allow a neutral car put in a neutral mode to go up or down. Then how will you verify? I said, no, that is not a problem. Verification is done very easily. I'll take a wooden plank or steel plank, put it on the road, giving a little tilt, and put any even ball or toy car. It should move up if it is true. Then came the reason should be there. Okay, before going to that reason, let us go to another phenomena which is also very prominently discussed, and it is that ulta pani. It is a place, of course, railway station also, where river water goes up. Now we have 2 points. I am not giving the answer, but I am making you to reflect on it. There can be two reasons. One reason, just I told you that on my front screen window, glass window, rain water was falling on window, on that glass sheet, and they were going up. So it can be there also in Ulta Pani, where water canal or in the tube goes up, which is a rare phenomenon. But it goes up, people say. But before that, we must verify it. We means not everybody cannot do all experiments. Believing also is one of the important things, and that believing should be genuine, verified. For example, many people post many experiments to me, and some experiments are so obvious that they are fake, and of course few are good also. And for that, when we see experiment it, we know more and more about it. When I was discussing this problem, are going uphill, one of my friends said, if you have done Cavendish experiment, then we see that those small lead balls are attracted by big lead balls. When center of gravity of those two balls are same, these are attracted and small torsion is produced on the um, hanging rod, which easily can rotate freely on either side. So that experiment was good enough to say that it is quite likely that something somewhere is very hollow. If land below us is hollow, there is small change in gravity. But we cannot say that now everything should move up. I believe nobody might have done it. Why only car? If I put a big lorry, will it go up? So probably the answer would be different. Instead of that, if I say no car required, I put a feather there in place of car or a small ball. It can also move up due to winds or different due to some other one or the other reason. If I have a feather, you can never predict that it will go up or it will go down. So similarly, limitations also should be very quoted. Now, let me see
Stop video now.
what Planck has observed. Planck saw something, some light is falling on a plate, kept, I can keep it on in the sun, or some light is falling and something, probably material particle, is coming out. Of course, Einstein did the other rest part and said, yes, it is electrons that are coming out. But Max Planck knew it. Then what did Raman observe? That when you have already Raman effect, he, of course, that is also known as the last confirmation for quantum mechanics. Quantum mechanics was quite early uh, discovered, you can say, but um, the final settlement of the result that yes, quantum mechanics is there, we call it Raman effect. And it no, so somebody is not, it is audible to somebody anyway. Uh, Now, what Einstein did, he also gave the light and something very great he said. It is not the intensity of the light, it is the frequency of the light that matters. So there was a difference. Earlier, before that particular photoelectric effect experiment, intensity means more and more intensity, more and more that cause should make result happen, which never was the reality. So when Raman discovered, there were two known effects. One was called Stokes and anti-Stokes. These two effects were already known. In Stokes, what happened? A higher frequency upon incident on the particular substance ejected a light of lower frequency. Whereas in anti-Stoke, light of some frequency when fell on a substance, the ejected photon is of higher frequency. Of course, that is very less uh, probability. People say 1 in 1 lakh, or we can say about 10 ppm. But those two effects were known, and hence Raman could show it on his spectrograph that both are there at the same time. So when excited atom gets further energy, a higher frequency can be expected. And if light falls on non-excited atom, it is quite likely that due to relaxation from one state to other state, the frequency goes down. Now, uh, one observation I wanted to say, that was also strange observation. When we say strange, there is nothing strange because we did not know much about it. So, what was that? General, in general we say whenever a substance is heated, its resistance decreases. But is it true for everything? No. In the case, it is not a fact which happens for all things. This is what happened, but in semiconductors, it was not that way. When semiconductor is heated, its resistance goes down. So, semiconductor brought revolution, revolution in the science industry, and then of course we knew magnets are made up of iron. Then we started saying ferromagnetic material. Now most popular magnets are ceramic magnets, which are something of this sort. So if you can see, these are different magnets, but ceramic magnets you can see here. This one. All magnets are ceramic only, but now speakers, loudspeakers or mic, they are using very light, comfortable, and um, rebuildable magnets. Just a few days ago, I noted, even that was in newspaper only. Good enough, good enough. Whittington and Yoshino got Nobel Prize for lithium batteries. What is this? What was special about it? Special was it was 30 times smaller is in size, and more powerful than ordinary Nife cells. How much? 22,000 times more efficient. Now I have started to believing that no machine can have efficiency more than 100%. Now it is quite likely that Carnot engine may not work when we go from one regime to the other regime. Of course, this should not be taken very seriously because it will break all the known laws. So be careful. It is just a wild guess. Why? What for wild guess? Because again, I'll use name of Feynman, and of course, I can make a, a statement which I used to hear from my venerable professor. Now, just a few months ago, he is no more. Professor Shivaraman of Sagar University. He used to say that if I touch a piece, small piece, if I touch by my fingers something small and take it out, what is happening? Maybe crores of particles are sticking on my finger, but it is not visible. Why? It is not visible because of our probes or instruments which we call extension of our senses may not detect it. Why? What is the problem? Then people say that if the concentration is less than 10 raised to power minus 7, our probes are not able to find it or notice it. But something has happened. When I touch, something has happened. And if I say about Feynman, he emphatically says, do not apply macro rules to microparticles. One of my colleagues, if he says, sir, I have seen this electron. Electron is here. No, brother, it is not there. As soon as we see, how do we see? Because something reflected from it comes to our probe or ourselves. That is what is happening, no? But when that something is reflected, where is the electron? It might have moved away some 20,000 kilometers. So it is just like saying that you go straight, then there is a buffalo sitting, you take right turn from that place. So this is macro example, and micro example. I'm sure it was here. That electron was here. That particular atom was here. It's not like that. So what Feynman used to say, not apply macro rules to micro stages. And for this, I will just introduce
Sir,
one more.
Bapat sir,
Uh,
gentle reminder, sir. So it is 10:45, sir. Our
okay,
next
just
speaker.
one more thing.
Uh,
I'll finish, but one more thing. Since
yes, sir.
I said lithium batteries are two kinds. One is lithium battery. Okay, it is not rechargeable. Efficient efficiency is there. Then lithium ion batteries are rechargeable. So that difference is to be there, and where aluminum also is used. So four things are there always in lithium batteries. So as you say, I'll stop, and then um I'll say that there is a uh, one more thing is that there is a um, carbon allot- allotrope which is called graphene, and it is nothing but monolayer carbon, and it is showing wonders, and many more new experiments without pollution may be expected in very near future. I'll stop here now. Okay, you can have something different or question over
Yes, sir.
question section.
Yes, yes.
Okay.
So thank you so much, sir, for explaining various concepts in physics, starting from Newton laws, Bernoulli's theorem, and lithium ion battery. So many things in explaining the students in a much easier way, and that too with some experimental evidence. We are teaching the basic concepts, and that too in a experimental way, which anybody can do it at any point of time. So thank you so much. So I welcome all the students. If anyone the participants, if any of them have any doubts, they can interact with us just for 1 minute only. Due to time constraint, and later if you have any other questions, you can just mail me or so that I can transfer it to sir.
Hi, sir. Good morning.
Hello, please.
Yes, sir. I had a small question, sir. How can we practically explain the phenomena of interference to students?
Okay, it is interference. I'll tell you, never happens single-handed. Everybody knows. For interference, at least two particles should be there. I am moving on a simple vacant road where nothing is there. I am moving. And when I am moving on the same road with a crowd of 1000, and let me move through that. Can I move in the way which I was moving when there was no crowd? I cannot. So it is macro definition of interference. But incidentally, such things happen at micro levels also. And there, that interference happens. Of course, logic is same, because when we have two holes, nearby holes, and passing electrons through it, a beam of electrons, then electrons interfere, and we have uh, that interference pattern on photographic plate. Of course, that is not visible to us, but other counters also can verify it, and that is what was done in Rutherford's experiment. If you remember, Rutherford is 5 pound bullet shell is reflecting by tissue paper. This is what was the experiment done by students, which is now known as Rutherford scattering gold foil experiment. Also, it is called. So, interference is that phenomena where I'm saying first in micro level, when two waves interfere or meet at some place, and at macro level, if I want to say, two particles, whenever they interact or they collide, you may not be able to predict the lines. But of course, when you use carom board and you are very proficient in playing carom board, you hit your uh, striker to a coin which will move according to your wish. So, in macro level, many things are controllable by human being, but at micro level, our agent or our probe is electron. Of course, now people say that if a moving electron or if a moving uh, alpha particle, then wavelength of interaction changes. So electron generally we take, but
Yes.
as our size goes on increasing, wavelength goes on decreasing.
Yes.
So
Thank you so much, sir. Thanks a lot.
thank you.
Actually, it's our honor to invite you and to have your talk on this workshop. I'm very grateful for you for accepting this offer. Thank you so much, sir. So
Okay,
now,
thank you very much.
yes, sir. So now
All
I move
all
on.
the university people, I am grateful to them.
Yes, sir. Thank you, sir. So now I welcome our next speaker, Professor K. Venkateshwar Rao, sir.
Okay.
So briefly, Sir is a professor of nanotechnology of Center for Nanoscience and Technology, Institute of Science and Technology from JNTU Hyderabad, and he has experience in teaching with a wide varies of subjects: quantum mechanics, nanomaterials, different characterization techniques, sensors, etc. And he did his postdoctoral experience from John Hopkins Medicine, USA, and PhD from University of Hyderabad, and Master of Technology from JNTU Hyderabad. And he has held several administrative positions from Book Bank Officer from
Madam,
Sir.
Madam, not required all these things. Can I start? Because
Okay, I understand. At least let me introduce our
yeah,
speak.
yeah,
Just a
yeah,
very small, briefly, sir.
yeah.
So,
Okay,
sir,
okay, thank you.
Yes. So has several of experience as a deputy warden and head of the department and additional controller of examinations, and he is a member of BOS for various institutions, and he has a lot of experience and he has several honors and awards. He is a MSc gold medalist and Raman postdoctoral fellow and best teacher awardee from Telangana government and ITAP award. In addition to that, sir has varied specialization of research, nanomaterials and applications of energy, sensors, agriculture and medical applications, biomedical applications. And he was a thesis advisor for 3 postdoc and 14 PhDs are awarded and 6 are ongoing. And his highly cited research papers are there in elsewhere. And he's also awarded with the Best Technical Research Paper Award by DMRL and overall around 250 publications, international publications, and around um, I think 7 research projects of national importance, and he has conveyed several meetings and refresher courses, workshops, and international conferences, and he has collaborated with various industries, and he visited various several institutions abroad also. So this is very brief biodata of Venkateshwar Rao sir. We are all very happy and honored to have you on our workshop, sir. Kindly proceed, sir. Sorry for making you delay for this particular slot. Thank you.
No worries, madam. Thank you. Thank you very much for your fruitful introduction, madam. And thank you very much for the opportunity. Very good morning to one and all, dear delegates and participants. Today, I'll be delivering you the takeaways after my talk are 2 important things. Number 1 is some of the properties of nanostructures. I want to concentrate today on optical properties. Basically, I want to tell you how you have to think when nanotechnology comes into reality. Means like experimentally. As sir told before, my Nandan Kumar sir told that you have to think not micro level. You have to think in a micro level manner, not macro level. Kind of understanding you need to know. For that reason, I will be talking some parts about nanostructures and then some experimental work on gas sensing and how you being I am also presenting today an MTech student thesis work, such that a postgraduate student can also do very good research. That is the 2 things I want to explain you today in the given time. So I just don't want to spend much time here, but however, the nanoparticles have got n number of applications, starting with textile, biomedical, healthcare, food and agriculture, industrial, electronics, environment, renewable energy. So there are n number of applications, quantum computing and biomedical and other things. But here gas sensing comes somewhere. So I'll be talking about chemoresistive gas sensing in the second part of talk. But however, in the first part of the talk, I want to answer you 2-3 questions for the students, basically at the level of graduation and post-graduation level students. The question is like this: why nano? Why not milli and micro? That is what my question. Because when smallness makes something, advantage of a smallness is when things are small, it can be more reactive. If that is the case, why we did not study 10 to the power of minus 3 meters and 10 to the power of minus 6 meters and directly jumped into 10 to the power of minus 9 meters, that is nanometer. And we did not study milli and micro technologies, and we directly jumped into nanotechnology. What made us to directly go to nanotechnology? That is the first aspect students need to understand. So here, these 2 things I want to concentrate in the overall talk. So let us take smallness. What is the advantage of smallness? Smallness may change its color. The gold is changed its to brick red. When you reduce the size of the particle, melting point will change, strength of the material will change, conductivity, reactivity, magnetic properties will change, and mechanical properties will change. These are all some of the things which will change. Why this is happening? That is the point you need to understand why the color of gold is changing to brick red when you reduce the size of the gold particles to the nano level. You need to understand fundamentally. If you understood fundamentally, you can think in a different way, and you can do research. You can do many. You can understand. You have to understand very fundamentally. Then you can do research in this area, especially in any branch of people. Why? Because it's a multidisciplinary course where materials and some applications. See, like now gold nanoparticles, and then this reduced size of gold because of plasmon resonance and because of these colors, people are using in n number of applications, mainly in imaging of cancer, protein imaging, especially when a patient get cancer or some diseases where you need to do a lot of PET, positron emission tomography, or other some biopsy kind of things. But with this of imaging with gold nanoparticles or quantum dots or silver nanoparticles, it will be very easy and simple. And the beauty here is you can image exact protein. What is the protein for which the lump is formed, and based on that, you could give the proper medication and treatment. That is the beauty of this type of fundamental properties. So first, I don't know, people might have already talked about, because this is a second day. I just want to give you in one dimension, which is less than 100 nanometer, a structure that is at least one dimension, which is less than 100 nanometers, can be defined as nanoparticle. They may be spherical. Sorry. They may be spherical or rod-like structure, tube-like structure. There are different types of structures are there. They're all called nanoparticles and nanomaterials. But however, the fundamental basic points are an important class of material with characteristic less scale less than 100 nanometers are called nanomaterials in any dimensions. If it is a two-dimensional, three-dimensional materials, if any dimension is less than a particular 100 nanometers, then we will say we defined it as a nanomaterial. And the beauty is exhibits novel superior properties compared to the microstructural features. This is another very important point you need to understand. Presence of significance of fraction of constant. Why it is that I will be explaining you in the next step. And but one more thing is it should be stable. So here, if I say nanomaterials, it should be with its characteristic length in one dimension should be less than 100 nanometers, exhibit novel superior properties, and a significant surface energy levels. I will explain this part in a very detailed way, and this should be also stable. Stable is very important point you need to consider, because when you reduce the size of the materials, the stability of the materials are going to be changes a lot. So this is another very important property a nanomaterial need to have. Nanomaterials derive their special properties from having one or more dimensions comparable to length scale, critical to science behind the phenomena. This is a very important point you need to understand, critical to science behind the phenomena. So I will not be explaining all the properties of the nanomaterials. I'll be explaining one or two properties such that you will understand how to think when you are in the nano level. So a simple example I just want to give you, if you take gold and if you reduce the size of the gold nanoparticles, there are different colors, starting with brick red, blue, dark blue, and like white, yellow color kind of things will happen due to such as optical phenomena, absorption, and plasmon resonance, and all other things. I will be explaining you in detailed manner. So I will spend 1 or 2 minutes here. So everyone, students, those who have got a pen and paper or notebook, try to solve along with me a simple basic problem I am going to solve along with you. Try to take a simple thing. I have a sphere whose diameter is 100 nanometers. Whose diameter is 100 nanometers. Now, I request all the audience, students, you take 100 meters or 10 centimeters or 1 meter, whatever you want, you take and solve the problem along with me. Now I took 100 nanometers and I am trying to solve the problem based on 100 nanometers. What is the formula for volume of a sphere? 4 by 3 pi r cube. Because I gave diameter 4 pi d cube by 6. So I substituted this value here and I got the volume 5.24 into 10 to the power of minus 22 meter cube. This is the volume of a sphere whose diameter is 100 nanometers. So you may calculate 100 meter, 10 centimeter or 1 meter, anyone you can take. And now I want to calculate the surface area of a same sphere. So surface area of sphere formula is 4 pi r square. That is nothing but pi d square. So I substituted it. Now I will ask you everyone for your 100 meters or 10 centimeters or 1 meter, try to find out surface to volume ratio. I will also find out surface to volume. So if I find out surface to volume on the numerator, it is 10 to the power of minus 14. On the denominator, it is 10 to the power of minus 22. And it comes to up, then it will be 10 to the power of approximately 7. Whereas in your case of 100 meters, 10 centimeter or 1 meter, this will not happen. This is the beauty. Once again, I'm repeating it here very carefully. Listen, everyone. See, if I am trying to find out surface to volume ratio in the case of 100 nanometers diameter sphere and 100 meters diameter sphere or 10 centimeter and 1 centimeter, you see here it will be approximately 1:1. Here also it is approximately 1:1. But in the case of 100 nanometers, some interesting phenomena will happen. This will be 10 to the power of 7:1. This is the beauty of surface to volume ratio, is predominantly increasing in the case of nanomaterials when compared to normal centimeters or meter scale. You might have already calculated, you might have already experienced it. So this is the exciting point and very beautiful point you need to first understand when you are talking about nanomaterials. Because so predominantly the surface to volume ratio is going to be increases. As the surface area to volume ratio increases, percentage of atoms at the surface and surface forces becomes more dominant. You need to understand it in like this manner. So you may also think even in the case of micro and milli, this may happen, but not that much predominantly. That is a very, very important point you need to consider. Generally, accepted material properties are derived from the bulk. Whatever properties we study at our graduate level and postgraduate level are basically based on the bulk properties. But when you are reducing the size of the materials to nanometer level, that is, then the surface to volume ratio modifications predominantly are going to happen. And because of that, percentage of atoms are coming more onto the surface. And because of that, surface forces are becoming more dominant. This is the first takeaway of my talk. That is what I'm trying to tell you is, when in the case of, I told you, when you take nanomaterials, the properties are going to be different. Why they are different? Because surface to volume ratio is increasing predominantly. Because of the surface to volume ratio increasing predominantly, the percentage of atoms on the surface are going to be more, and hence surface forces are going to be dominated. Because of that, the nanomaterials show a different type of properties. This is the first takeaway of my talk. And coming to, if I see, I just want to tell you if it is 1 nanometer, 10 nanometers, 100 nanometers, 1000, like that, and how the surface area is going to be modified. I just want to show it to you. Surface to volume ratio is going to be predominantly changes will happen when you reduce the size. Similarly, same example, you can take a cube, and you also know the formula for a cube and surface area. Volume is length into breadth into height, and 6 into length into breadth, 3 phases. You have 2 phases. So based on that, if you calculate surface to volume ratio in a different way, I want to tell you, take 1 centimeter by 1 centimeter, and you go on cutting into pieces to nanometer level, then you can cover a football ground. That means if you are going on calculating total surface area to volume ratio, it will be very, very high. That is what I want to mention it to you here. However, before this talk also, speaker told that how to think quantum mechanically when electron is there. When classical mechanics cannot answer all the questions. So you need to understand the quantum confinements, quantum confinement effects, and thermal fluctuations, discreteness of the matter. All these things are very, very important to understand nanomaterials. This is another very important graph I want to tell you. Let us size of the particle, diameter of the particle on the x-axis, and surface to volume ratio on the y-axis. Surface to volume ratio on the y-axis. So 10 to the power of 9, 10 to the power of 6 is nothing but it is millimeter, 10 to the power of minus 3. Am I right? Because the scale is in the nanometer range. And it is micrometer, 10 to the power of minus 6 meters. And see here, at 100 nanometers, something predominant is happening. Till from the starting point to till here, there is no surface to volume ratio increase happening in the case of micro and milli level. But after beauty is happening in between 100 to 1 nanometer. That is, there is a predominant increase in the surface to volume ratio. Are you following it? And this is the beauty. And because of that, the properties of the materials are going to be modified as the surface to volume ratio predominantly increasing in between to 100 nanometers. So till now, I only told one very important point, that is surface to volume ratio increasing. And I took a simple example of a sphere and cube, and I tried to explain you. So now you can answer me, why not milli technology, 10 to the power of minus 3 meters we studied, and why not micro technology, 10 to the power of minus 6 meters we did not study. Why? Because there is no incremental improvement in the surface to volume ratio. But whereas in the case of 100 nanometers, that is happening. That is the reason we are all studying about nano. Nano is one, that is the beauty of nano. That point you need to understand first. And the same graph, if I take from 100 to 1 nanometer, there is a incremental improvement. Same from this part I took. Only from this part, if I draw a graph, there is a full increment is happening. This is the point I want to explain you, everyone. I assume that you understood it very clearly. If you have any problem, please put it in the chat box so that I can see that and I can answer the questions. Okay. And time is not sufficient, so I just don't want to go here. So the basic thing is examples of unusual properties of materials are lowered phase transition temperature, increased mechanical strength, different optical properties, altered electrical conductivity, altered magnetic properties, unique biological responses, unique chemical reactivity. These are all some of the unique properties that will happen at a nanoscale, which will not happen in the case of bulk materials. You need to understand why, because I will take a simple example. I can also take about crystal structure, but it will take a lot of time. You need a lot of physics actually. So for the sake of understanding, I will take some simple example and I will explain you how to think in a different way. So let us take optical properties, because you can visually see it. The beauty of optical properties are, you can see they are in the visible region, in different colors will be there. So you can see it visually. So modification, there will be a mechanical property changes, optical, electrical, chemical, and magnetic property changes will happen. So let us take another very important point I also want to mention you here, morphology. Don't worry about the morphology. It is how they look. Sometimes they look like a plate, sometimes they look like laddu, sometimes they look like in a different formats. Based on this also, there will be a different properties. At this point of time, I don't want to talk about that. But however, let us consider, I will just give you a little, another 5 minutes I will be spending you on optical properties. So if I want to talk about an optical properties, you need to know what is a plasmon, surface plasmon. It's basically, if you think classical electron free theory or quantum electron free theory, electrons will be there and holes will be there, and electrons or holes or positive or negative things will be there. When a light is falling on that, light is nothing but electromagnetic radiation. Electromagnetic radiation can be represented as electric field, applied electric field. Due to this applied electric field, there will be a cloud movement will be there. That means all positive will come to one side and all negative. You know very well, two opposite charges will be attracted because of that influence of this electromagnetism is nothing but light with a wavelength of visible region, and then they are nothing but photons, hnu, you know very well. So when they are coming here, because of that, there will be a displacement, or there will be influence. Because of the influence of electron, the fluid will move, that the electron fluid will be moving. And when the fluids are moving in the electric field is oscillating like a photon. See, because when your photon is nothing but electromagnetic field which we are applying, then the sea of electrons will oscillate too. These oscillations are quantized and resonate at a specific frequency. Such oscillations are called plasmons. If this oscillation is in the visible region, then you could see different types of colors. Especially gold and silver plasmon resonance are in the visible region, and because of that, you could see different types of colors like brick red, yellow, blue kind of colors. So this is the basic fundamental thing. Plasmon resonance is a fundamental thing. And when you are reducing the size, plasmons are the coherent excitation of free electrons in metals. But however, I don't want to go in detail. But what happens is, because of this particular plasmon resonance, the spectral location, strength, and number of plasmons resonance for given particle depend on the particle size and shape. So when the size and shape is going to be modified, and you could see different types of colors, same gold, but due to the size modification, the plasmon resonance is going to be modified, and it is an inherent property of that particular material. And because of that, they're different. Even shape, if it is circular and it is triangular, there are different. If it is sphere and hexagonal, rectangular, there, depending on the type and shape of the particle, the absorption or phenomena or the plasmon, surface plasmon shape depends on absorption of spectra. And because of that, you could see n number of things. Why? Because I took optical is you could understand it very clearly. See here, quantum dots, same material with size difference. This is the beauty of optical quantum optical phenomena in the nanomaterials. So similarly, photonic crystals, same material, when you are zooming it, you may also ask another question, sir, why nano now, why not earlier? Earlier is also nano is there. Why? Because now the different types of microscopies are available, like electron microscopies. There are different types of TEM, SEM, the kind of missions are available. Now we could see atom by atom and molecule by molecule. And because of that, this type of properties are going to be modified. Similarly, I don't spend much time here. Electrical properties. Basically, the electrical properties are going for nanomaterials, they are going to be entirely different based on the length of the charge carriers. This is very important. So silver has got a charge carrier 53.3 nanometers. So if below that, its electrical properties are going to be modified. In the case of copper, 39.9. So these properties are going to be modified. That is the way you need to understand in the case of electron transportation. And then melting point also, as the material's melting point size is reducing, it decreases. And once again, based on the phonon concept. Phonon interaction will be there, and based on phonon mean pre-path length, the melting points, how they are going to be reduced, and based on that, you could also talk about thermal properties of the nanomaterials. I don't want to go for magnetic, but this is so here. Till now, I told you 2 points. Someone please switch on their mic. Please mute the mics, everyone. Dear students, please mute the mics, everyone. So here, I want to, till now I told you 2 points. Gandhi Chandrasekhar is speaking in the thing. Please, could you meet Gandhi Chandrasekhar Garu?
ఫోన్ లేకుండా ఎట్టుంటది మా
Gandhi Chandrasekhar Garu, could you please mute your phone?
మీకు ఫోన్ లేదా ఇంట్లో ఫోన్ లేదా
Gandhi Chandrasekhar Garu, could you please mute?
ఆ నెంబర్ అని చెప్పు
Okay, so here,
తీసుకురా రేపు తీసుకురా
yeah. So here till now, I just tell you 2 points. Till now I discussed 2 points. The first point is when you reduce the size of the come to nanomaterial, surface to volume ratio will be increases predominantly, and because of that surface particles will be coming onto the surface, and because of that surface energy levels will be increases, and because of that thermal, mechanical, electrical, optical, other properties are going to be changes, and that you need to understand in a scientifically in a fundamental way. Then you can do a lot of research. And coming to the nature, you see the peacock feather, they are always looking bright in color, and different colors will be there, and all these things fundamentally from our physics level, contact angle, surface tension phenomena. But now if I start zooming it, you could see a nano size holes repeated as a pattern of nanoscale. So if I can design this kind of morphological material, so I can create this type of material where when sunlight falls, it will be looks different in colors and self-cleaning, and no one is cleaning peacock feathers. In spite, they look in very bright in color. So basically, I want to tell you here is nature is the very beautiful thing. Being a science student, being an engineering student, being a technological students, we need to see nature in a different perspective, such that you can engineer or you can biomimic the nature, such that it will be useful for the mankind. You know very well, apple is falling before and after also, but one boy came and told that apple is falling due to gravity. So the way you look at the falling of apple is he only looked in a different way. That is where the scientific explorations will come up and new things will happen. Similarly, another example I want to take, lotus effect. Based on that, you know very well surface tension and other things, but if I zoom it, you could see very clearly there are some nanoparticles. As on today, different types of anti-fogging materials people are developing it, such that it will be useful for mankind. So whatever science we are studying, it is simply biomimicking. And coming to the nanosensors, I just don't want to go fundamental things. I have a lot of videos and other things, but sensors are used everywhere. Even in Hyderabad on Saturday and Friday, police will be very busy to catch up the drunk and drive people based on gas sensor. It is a human exhale gases basically. So sensors are used everywhere, almost everywhere. Environmental, like continuous monitoring of patients, and then in cars, almost all the parts of cars, and manufacturing, defense, space, and household things also. There are a lot of things are there. I have a small video here, but I will share it Mamata madam. You can see individually because I don't want to waste much time here. So coming to a sensor is a converter that measures the physical quantity and converts it into a signal which can be read by an observer or by an instrument. Basically, a sensor is an instrument where a physical phenomena can be measured. I can say how to measure a physical phenomena, maybe velocity. There are two types of, generally broadly, I can divide two types of mechanical and electrical. In the case of mechanical, velocity, acceleration, force, pressure, temperature, these are all some of the energy related sensors: current, voltage, capacitance, inductance, resistance. There are this kind of another missions. Even a sensor requires physical parameters and converts it into optical, electrical, mechanical signals which are suitable for processing. So basically, it's a physical phenomena where you are using some instrument. That physical phenomena could be measured in a different format. I will be explaining it to you very clearly. Now I will be talking about chemoresistive gas sensors. That means in this phenomena, I will be measuring resistance. So gases and resistance. So I am using some gases, and then I want to measure the resistance in the circuit such that I want to sense the gases. That is what I will be talking in the next few 10 minutes. I will be taking extra 5 minutes, madam. So in the olden days, actually, people used to use different types of lamps. Like in mines, people want to go, then they use this type of lamps. When there is no oxygen, lamp will be switched off so that people understands that there is less oxygen. And otherwise, there are birds people used to take, and if bird is unable to breathe, bird is not coming back, and in the mines, workers know that it is not good actually. So I'll be talking. This is another very important slide I want to. Before this, I'll just go to another slide. Here, a simple experimental setup I am showing it to you. Very simple experiment. What is this? Is I am coating some nanomaterial here, and I want to measure. Let us say I want to measure LPG gas. In the home, everyone will have an LPG sensor. Everyone will have LPG gas cylinders we are using very well. And we are using gas sensors. We are using LPG cylinders in our home world things. So when you are sending this gas here, and this is the nanomaterial, and a little amount of voltage I need to give for the circuit. And here, you know very well a multimeter where I can measure the resistance. This is a simple setup you can design. So what happens when the gas is coming onto the nanomaterial? The two phenomena will be there. One is it may oxidize or it may reduce. These are all the only two phenomena or possibilities are there. So here I'll just take, depending on the type of the material, I may use N-type material, I may use P-type material, but however, when the gas is coming to this nanomaterial, so the material may oxidize or reduce. That means it may give electrons or it may take electrons. These are only two simple phenomena we have got. So, and what I am telling you, I connected this onto a multimeter where I can measure resistance in the circuit. So what is happening? The resistance may increase or resistance may decrease, depending on the type of the material what I am using, and depending on the type of the gas what I am, depending on the phenomena of the gases, like it may be oxidizing or it may be reducing, N-type and P-type. So there are only four possibilities are there. Resistance increases, resistance decreases, resistance decreases, resistance increases fundamentally. These are all some examples of different types of gases and N-type and P-type material. So what happens here? Basically, these are the four possibilities are there. Resistance may increase, resistance may decrease, resistance may increase, resistance may decrease. So depending on the N-type and P-type. So don't be confused. I am here. This is the third point I am talking. The third takeaway. The first takeaway is nanomaterials or surface to volume ratio increases predominantly. And based on that, all the molecules are on the surface, and because of that, surface forces are more, and because of that, all the properties of the materials are going to be varied. That is the first point I was discussing. And coming to the second point, I was trying to tell you, everything is nature. Try to understand, see the nature, and from the nature, you have to understand science and technology. That is the second point. Coming to the third point, what I am trying to tell you is, I am working on gas sensors. What type of gas sensors I am working? I'm sending a gas, and I can measure current, I can measure voltage, I can measure resistance. But you may ask, why you measure resistance? Because it's a simple way of doing an experiment. I developed a setup in our lab. Actually, we developed a setup in our lab actually, where we can measure different types of gases actually. So I want to measure, if I measure resistance, it will be a little easy when compared to other things, but there are disadvantages also there with the respect to chemoresistive gas sensing. For that reason, I am trying to explain you. In that gas sensing, what is going to happen? There are two phenomena are there. When on the materials, gases are coming, they may take the electrons or they may give the electrons. That means oxidization or reduction phenomena are there. So based on the oxidization and reduction phenomena, there is a possibility of resistance increase or resistance decrease, or resistance decrease or resistance increase when I am sending the gas onto the materials. This is the fundamental point I was trying to explain you. It's a very simple point. This graph I want to show you, and then, so possibilities are what? If I am using N-type material, and if I am using reducing gas, then there is a possibility of conductivity increases. If conductivity increases, resistance decreases. It's a simple way of understanding. Another possibility, N-type material and oxidizing gas. Then conductivity decreases. That means resistance increases. Another possibility, third possibility is if I am using P-type material and reducing gas, then what is the possibility? You know very well. Here, conductivity decreases. As conductivity decreases, resistance increases. And what is another next step? You might have already known, that is once again P-type, and oxidizing gas. Here also you know the answer very well. You might think, because here resistance is, conductivity is decreasing, here conductivity will increase. And hence resistance will decrease. These are all the fundamental things. But however, you should also know another very important point. What are the parameters of a sensor? Materials perspective. Chemical composition of the material should be good. Crystal structure of the material, catalytic activity, surface structure, morphology. This particular, one of my recent PhD student, only one MOO3 material, but we did on MOO3 material. We modified morphologies, 7-8 types of morphologies, and we are trying to understand how the sensing properties of MOO3, gas sensing properties of MOO3 modifies with respect to the materials. This is one aspect of parameters of materials. Coming to the parameters of sensor elements, thermal stability should be very good. Selectivity of the gas response should be very good. Selectivity of the gas means, let us say you designed a sensor for alcohol breath analyzer, and one person took a coffee or tea and it is showing some results. Then what is it working good? No, its selectivity is not good. It should only select alcohol, and it should only give the breath analysis for alcohol. Gas sensitivity should be very low sensitivity also. How much sensitivity? Let us say one person drunk little and one person drunk heavily. And if you keep the breath analyzer, you should know who drunk less and who drunk high. You should not give same results for the same things. And operating temperature should be low, and rate of response should be very, very good. These are all the response parameters for sensor, and these are the materials properties. And then simple calculations and basic terminologies in sensors comes here. If you send a gas, it is a time and it is a resistance. I told you, I am going to measure the resistance. So graph will be like this. Okay. And here, this is the term response time, because I will show to this graph. This will be very easy. See here, graph is like this. So what happened? Graph may be this or maybe this, because it may increase or it may decrease depending on the phenomena and depending on the type of the material. So this is the response time. So when I am setting gas, first it's decreasing, it may increase also. And this is the response time and saturation. And when I remove the gas, it should come to normal state once again. This is the recovery time. Recovery and response time should be very, very small for the materials. So response and recovery time. Sensitivity is nothing but RA is in the air resistance, and when I'm send the gas, that is the resistance divided by RA. And selectivity, response time, recovery time, long stability. These are all some of the very important parameters you need to know when you are talking about a sensor. I repeat it here once again. I am trying to tell you, Mamata madam, I will take 5 more minutes. Sorry for the inconvenience. So here, first point is like you need to measure the resistivity sorry, there are four possibilities are there. Resistance may increase, resistance may decrease depending on the N-type or P-type, oxidizing and reduction phenomena. And this is the simple basic circuit you have. And then this I already discussed. And then I'll directly go to another material. So simple, it's an MTech student's work. These are all IEDs, interdissociated electrodes, where we coat the nanomaterial here. And this is the flexible sensors. We also coat the material here. This is the setup which we have in our lab. These are the flow meters, gas sensors. These are the flow meters. This is the chamber. In the chamber, we will keep the, we coat the nanomaterials, whatever we prepared on the IEDs, and then we coat it here, and then we collect it here with this meter. I told you resistance. It will be 10 to the power of -6 ohms. Measure difference also could be measured, and a computer, a vacuum pump is there, and based on that you can measure. It's a simple basic work done by our MTech student SM203. We did hydrothermal template assisted synthesis of nanomaterials based on eggshells we took, and then that we did it in a simple hydrothermal method. And these are X-ray diffraction, FTIR, X-ray diffraction, you know very well, crystal structure, and FTIR for group, what are the groups are presented, UV. So you could see different morphologies like rice-like structures and small rod kind of things. And then big rods, rods with more diameter, a flower kind, and hierarchical structures, hexagonals, same material, but we could prepare in a different formats of same with the modifying hydrothermal modifications. And then we coat the prepared nanomaterial using a drop casting method onto the IEDs. The IED will be looking like this, and we connect it, the IEDs in the circuit. IED will be kept it here, and then we will see first what we do. We will be measuring the concentration versus response, resistivity, and then we go on increasing it. And this is the response time, and this is the recovery time we'll be measuring. And selectivity, like if I use ethanol, acetone, NO2, CO2 kind of thing, what is going to happen? The selectivity should be more for LPG. It is in the case of LPG. And these are the results. I just don't want to talk about the second case study. And I work in Jawaharlal Nehru Technological University, which is in Hyderabad. We have 8 constituent colleges in JNTU, Hyderabad. And I work in the Institute of Science and Technology, which is in Hyderabad, basically in Kukatpalli campus, where we run 8 different centers are there. I work in DST Nanomission Center, DST sponsored Nanomission Center, as a professor of nanotechnology. We run MTech in nanotechnology and PhD in nanotechnology. We work on energy, battery, material applications. We also work seed germination and agriculture related works, and anti-cancerous, because it's a collaborative work, and antibacterial things we'll do. Our basic work is on sensors, glucose sensing, gas sensing, humidity sensing is the broad areas where we work. And then these are all some of the instruments, facilities we have, like X-ray diffraction, atomic force microscopy, TGDTA, FTIR, contact angle, cyclic voltammetry. These are all some of the instruments. These are all some of our PhD students who completed 15 students PhD completed, and now there are 6 students are working with me. And thank you very much for your attention. If any questions are there, I'll be very happy to answer. Thank you.
Hello, sir. Good morning, sir. Very nice presentation.
Yeah, good morning, please.
Sharing for upcoming researches. So I have one small query, sir. How to influence the optical properties, one-dimensional and two-dimensional, three-dimensional molecular nanostructures, as well sensor applications, sir? Which one also higher activity among three-dimensional?
Sir, the question I understood, Kodeshwar sir, the question is like this.
Yes,
First part of question is, you are asking me how to use enhance the optical properties, and you want to use them in sensors. Am I right, sir? That is the question you are asking?
Yes, sir. Yes, sir. Yes, sir.
Okay, sir. Optical sensors are different areas. Are basically there are different types of optical sensors people are working because it's a once again it's a very broad area. You can see a lot of literature is there. Basically, size engineering you need to do. Let us take in the case of gold, if it is 4 nanometers, its plasmon resonance is different. If it is 10 nanometers, its plasmon resonance is different. If it is 3 nanometers, its plasmon resonance is different. So that much accuracy you need to have when you are going for a device. That is the basic disadvantage, and the problem as on today is upscaling the things. Like if I could prepare a nanomaterial of 1 gram or 2 gram, but I cannot prepare the nanomaterial of 1 kg or 2 kg, because the process engineering is a very tough task. So the chemical engineers and process things are required very much. That is where the big problem we are facing. As scaling up is the very big tough task, sir. Actually, the question you asked is very broad question. I cannot directly answer in one or two things, because there are fibers people are using in optical sensors. There are a lot of fibers and a lot of nanomaterials people are using. And not only that, even switching of lights directly, like sunlights are like wall, like when sunlight falls on it, automatically energy conservation. There are many things people are working.
Okay. Thank you, sir.
Thank you very much, sir.
Thank you so much, sir, for your excellent talk and explaining nanomaterial properties and explaining sensors and its mechanism in a simplest way to all the participants, and who are all beginners also could get exact view of it. Thank you so much, sir. And there might be some more questions. I request all the participants that I'll give sir's mail. Maybe you can send me also. I can direct it to sir.
Yes, madam.
Thank you
Please,
so much, sir. And
if
we have
any
taken
chat
extra
box is
time
there,
of yours.
if chat box is there, you send me, madam. I'll try to answer the questions also, madam.
Hello.
Okay?
Could you hear me, sir?
Yes, madam. Yes, madam.
Yes. Thank you, sir. Thank you. So, all the participants, now I request you to be ready. So we have the next talk. So next talk is by Dr. Preeti on photocatalytic hydrogen production from industrial hydrogen sulfide. And I'm sure all the participants would have enjoyed the previous talk, and whoever has any questions, you can just send me in the chat box, or you can also send me. So I will direct it to Professor Venkateshwar Rao sir. Sir will be very happy to answer any queries on the topic. Due to constraint with the sir's schedule, I couldn't ask all the participants to convey your queries to him. So kindly please note that particular point. So for the next sessions, please be available to ask, and whatever the questions you had it on the previous session, you can send me through chat box, or you can also send me by mail. Thank you. So now let me introduce Dr. V. Preeti. She is Associate Professor in Renewable Energy Lab, Department of Civil Engineering, Hindustan Institute of Technology and Science. Dr. V. Preeti received her PhD degree in Environmental Engineering from Anna University, Chennai. She completed her MSc in Environmental Technology, Autonomous University of Barcelona, Spain. And her main research activity is concerned about advanced oxidation technologies for waste gas, wastewater treatment and hydrogen production, air quality modeling, and waste gas treatment by biofiltration, biogas production from waste, and photocatalysis for environmental, energy, and health applications. And she has several publications, peer-reviewed publications of international review to her credit, and she has communicated 25 oral presentations in international conferences, and she has 3 patents, and she was awarded with the Young Scientist Award for Hydrogen Energy and Advanced Materials by NIT, And apart from that, she also received 5 national and international awards for her innovative research findings. And she has worked also as a researcher in IITM and UAB Spain. And she has around 13 years of experience in both research and teaching. And she has organized and conducted 2 international conferences on sustainable energy and environment, funded by DST, Government of India, and she is also principal investigator for the project titled Recovery of Hydrogen from Industrial Waste Streams, funded by DST. So this is her short introduction. I welcome all the participants for the presentation of the Dr. Preeti ma'am. Ma'am.
Thank you,
Hello,
ma'am.
ma'am.
Thank you for the nice introduction and good morning. My topic is photocatalytic hydrogen production from industrial sulfide, hydrogen sulfide waste. My presentation includes introduction, industrial waste, hydrogen sulfide, case studies, treatment techniques for hydrogen sulfide. Both includes conventional, non-conventional techniques, and how to recover hydrogen from hydrogen sulfide waste, and conclusion. So hydrogen sulfide is a toxic gas emitted from both natural and industrial sources. And natural sources, mostly volcanic eruptions, etc. And from industrial sources, mostly from petrochemical refineries. And you can see the image of the amine samples. And the amine samples mostly ethanol amine, diethanol amine, and you can see the fresh amine solution, which is colorless and which is used to absorb the hydrogen sulfide. And you can see the poor amine, that is 1 to 10% having hydrogen sulfide, and then more than 10% it will be called as rich amine, and you can see the dark yellow color. And these are the other sulfides naturally found around volcanic eruptions, etc. And these are the properties of hydrogen sulfide and sulfide. Hydrogen sulfide in gaseous phase exists in pH 4 to 8, and the liquid phase hydrogen sulfide from 8 to 12 in HS minus hydrogen sulfide ion form. And sulfide ion, it exists in pH 12 to 14, and it has high uh, rodent egg smell, and it's flammable, colorless, and soluble in water, and which is extremely toxic gas, and also corrodes pipelines and also affects the aquatic life. And it has natural sources which is emitted from natural gas, petroleum over the surface of it, and volcanic gases, and then decomposition of organic materials by bacteria also gives off hydrogen sulfide gas. And the sulfide wastewater, which is also found in saline marshes and sulfur springs, and also found in low lying areas. And the industrial sources, you can see it is coming from petroleum refineries, leather tanning, pulp and paper, and sewage treatment plants, and petroleum refineries. It is coming from hydro desulfurization unit, where hydrogen gas is used to purify the crude oil or the oil, and while purifying the sulfur present in the crude oil, the sulfur mixed with the hydrogen produces large quantity of hydrogen sulfide. And in leather tanning, you can see while unhairing the leather, the skin of the animal, removing the hair, the sodium sulfide is added. And in case of biogas scrubbing unit in STP, also sodium hydroxide is used to scrub the sulfide gas, which is coming from the anaerobic digester. And also you can see in pulp and paper craft process. In craft process, also sodium sulfide is used to digest the wood, and the sulfide get mixed with the water and forms sulfide wastewater. And the effects of hydrogen sulfide from 0.1 ppm onwards, it causes effects like 0.1 to 10 ppm. It causes eye, nose, throat irritations, and up 10 to 50 ppm it causes severe headache, and above 100 to 300 ppm it affects the olfactory nerves and causes loss of sense, and above 500 to 1000 ppm it or even causes death. And other environmental effects includes corrosion of pipelines, concrete, steel structures, etc. And also it affects the animals, birds, and other aquatic life. So these sulfide wastewater, both in liquid phase and gaseous phase, has standards. In liquid phase, 2 milligram per liter is advisable or permissible limit, and you can see the gaseous phase like 150 milligram per meter cube in case of refineries, and for other STP and tannery, it is 5 milligram per meter cube. And it can be able to analyze, or it can be able to detect the concentration of hydrogen sulfide in working environment with the help of lead acetate or coated strips or calorimetric tubes or electronic portable and fixed monitors. And also by use of gas chromatograph, it is possible to detect the concentration of hydrogen sulfide. And in industries, people used to have alarms in order to find out the concentration of hydrogen sulfide in large areas with the help of colored lamps. And other respiratory protection can be used in case of refineries and other industrial purposes. And by providing the oxygen cylinder at the back, also we can use the oxygen and to protect. And then also some kind of back mounted tanks, and with the help of large hose lines also used to protect. And other case studies worldwide, due to which the hydrogen sulfide accidents caused in case of several accidents were happened. A few we will see in as case studies. During the year 2009 in France, in petroleum refinery, while working with the hydrogen sulfide maintenance operation tank, 3 employees were injured, and also one died. And also during the year 2007 in United States, while the treatment and disposal of hazardous waste, in case of landfill, it closed environment due to anaerobic condition, and while repairing the pump in sewer, 4 employees were died. And also in United States, also the due to failure of valve, 2 employees were affected, and one died. And in case of Germany during 2007, due to 1275 kg of hydrogen sulfide release, several people were affected. And during 2004 in Germany, a release failure of pump, also due to which 2 employees suffered. And 2006 in Germany, in refinery also, due to the leakage or failure of leakage of hydrogen sulfide due to failure of valve, again 46 employees were injured. And Germany again in 1979, in coking plant, the release of hydrogen sulfide was observed, and it affected. Similarly, during 1976 in Germany, in case of wastewater treatment plant in anaerobic digestion unit, hydrogen sulfide gas released. And during 1969 in Germany, in refinery in flaring unit, the release of hydrogen sulfide was observed. And also during 2006 in chemical industry, Kolkata, India, cobalt sulfide unit accident happened, and 2 persons were injured. And in case of UK during the year 2006, the double fatality happened due to distillery biological effluent treatment plant. And during 2007, 17 cattle died, and due to leakage of 500 kg cylinder of hydrogen sulfide, Again, several people got injured and got affected. Similarly, STPs and other refineries, also several incidents and death happened. So these are the case studies from which we can see that several accidents are happening till date because of this toxic hydrogen sulfide, and it is very important to treat the hydrogen sulfide, and it is very important that to remove the or increase the percentage of removal. So there are several research happening in order to remove the hydrogen sulfide from this toxic emissions from industries. So there are several techniques available, conventional techniques available. In case of gas phase treatment, there are several treatments available, physical, chemical, and biological. Under physical treatment, absorption, dilution, then scrubbing, etc. And chemical treatment like scrubbing, neutralizing agents, and thermal oxidation are used. In case of biological treatment, activators, sludge aeration tanks, and biofilters, then compost filters, sand and soil filters, trickling filters were used to treat the hydrogen sulfide gas. And in case of liquid phase treatment, physical and chemical methods are used. In case of physical treatment, aeration method is used, and in case of chemical treatment, chemical and precipitation methods were used. And the mechanical and operational HTS removal is also possible in case of industries, and the small concentration of hydrogen sulfide will be flared in case of refineries mostly. And then the stripping process is used to extract the hydrogen sulfide from liquid phase to gaseous phase at high temperature and pressure. And membrane separators also used to remove the hydrogen sulfide. So other chemical sulfide, hydrogen sulfide treatment includes adsorption, in which activated carbon and other medias, natural medias, are also used in order to adsorb the hydrogen sulfide. But in case of adsorption over a period of time, the particular media should be regenerated and should be used. In case of scrubbing towers, there are several types of scrubbers used, like iron sponge, iron oxide pellets, activated carbon, water scrubbing, sodium hydroxide scrubbing, biological removal on filter bed, etc. But mostly iron oxide is used to scrub, in which the iron oxide reacts with the hydrogen sulfide gas to give iron, and then this iron sulfide will be oxidized and sulfur will be separated, and this sulfur can be used in several industries. And hydrogen sulfide can be directly scrubbed in sodium hydroxide to get sodium sulfide. Further, the sodium sulfide can be used to treat effectively to remove the sulfide. So it is better to treat the hydrogen sulfide in liquid phase than gaseous phase. And if we take biofiltration, which is coming under biological process, and the microorganisms will be used to remove the hydrogen sulfide present in the industrial waste gas. And the media biofilter, several types of biofilter media is used. Based on the economical condition, it will be used, and the microorganism will be attached to the biofilter, the media, and it will be consuming the nutrients supplied over the surface of the media, and it will be growing over a period of time. It will be effectively treating the hydrogen sulfide gas. That means it will consume the hydrogen sulfide and will be releasing the free gas or air. And this is a closed process, which is a conventional process mostly used in refineries to treat the hydrogen sulfide. The hydrogen sulfide, initially it will be going inside the combustion chamber, where high temperature like 1200 degree and above will be maintained, and about 30% of hydrogen sulfide will be removed, and the balance 70% of hydrogen sulfide will be taken to the aluminum oxide chamber, where it is oxidized and the sulfur will be separated. can see the temperature maintained is 1350 degrees centigrade, and it will be burning the hydrogen sulfide initially, and then finally the balanced hydrogen sulfide will be taken to the aluminum oxide chamber, where it will be oxidized to sulfur, and this sulfur can be utilized in other industries. Other non-conventional techniques includes thermochemical methods and electrochemical, photochemical, catalytic thermal dissociation, microwave plasma dissociation, etc. But this requires more energy and more pressure, more like it consumes more energy, and while splitting, it also gives off toxic gases, greenhouse gases, whereas photocatalytic process requires very less energy, that is 33 kilojoule per mole only, and also that too can be utilized from the solar light and can be converted into useful hydrogen and sulfur. So this photocatalytic process has both economical and environmental benefits. So we can compare the conventional process and current photocatalytic process. And conventional process, like glass process, only sulfur can be recovered, whereas hydrogen is wasted as water. Whereas in photocatalytic process, both hydrogen and sulfur can be recovered, that too when very less, with very less utilization of energy, that is 33.44 kilojoule per mole. So these are the properties of hydrogen. It's a colorless, odorless, and light, which is lighter than air. So it produces harmless end products while burning. That means it gives off only water vapor while burning, and it is non-toxic, poisonous. It is non-poisonous gas, which is cheapest, and which is cheapest energy carrier in near future, and storable and transportable, which is environmentally friendly, clean energy fuel, and can be used in cooking and food industries, heating purposes, and other welding, chemical, oil refineries, and transportation purpose, and also in other sectors like electricity generation, then detergent manufacturing and fertilizer manufacturing. So when we see the energy statistics, according to the energy statistics, we are running out of fossil fuels, and in next 50 years there won't be any fuel available, so we have to concentrate on renewable energy sources. And that too, renewable energy sources, when compared to other like biomass, wind, etc., we are using the solar energy in very less percentage. So we have to increase the percentage of solar energy utilization. Since India receives maximum solar energy, India has large solar energy potential, that is 600 trillion watts. So it should be utilized, and it should be used for recovering hydrogen from hydrogen sulfide. When compared to other fuels, we can see hydrogen has high energy content, that is 119.9 kilojoule per gram. And this hydrogen is produced from fossil fuels. That means 95% of hydrogen is produced from steam reforming, that is using naphtha or non-renewable sources. And this that means fossil fuels, and also use of more greenhouse gases. And other techniques to produce hydrogen is water source is water, that through electrolysis, then thermochemical methods, and biomass also used to produce hydrogen, gasification and microbial, but it requires large time and requires more energy also. So when compared to that, photocatalytic process, best process for recovering the hydrogen. And this is the mechanism of hydrogen production. Both liquid phase and gas phase is demonstrated, and you can see this is a photocatalyst, and the photocatalyst having the band gap energy in between. So when the sunlight comes contacting with the photocatalyst, the electron jumps from the valence band to conduction band, thereby releasing the electrons and holes. the holes oxidize the sulfur, the hydrogen sulfide to sulfur, and the hydrogen sulfide, the H plus ion will be reduced to hydrogen. So this is happening in case of gas phase. In liquid phase, the hydrogen sulfide ion will be oxidized to polysulfide and hydrogen. Otherwise, we can use this polysulfide to convert it into sulfur, and then further the hydrogen ion will be converted into hydrogen by electron. The electron will be reducing the hydrogen ion to hydrogen gas. So several literature review have done and found that several types of photocatalysts were used for converting the hydrogen sulfide, that means sulfide wastewater, to hydrogen gas, and some like percentage, how much percentage of conversion is observed, and we can see in the year of 2002, Atif Kofa used cadmium zinc sulfide, and the concentration used is 7,680 ppm, but the percentage of removal, the percentage of conversion is 83%. When compared to the other things, the conversion is very less in case of other photocatalysts. We can see 4%, then 2.4% in case of spinel photocatalyst, and so then other ruthenium and metal oxides were used, and so this percentage of conversion is not only based on the photocatalyst, but also it is based on the concentration of hydrogen sulfide we are using, and also the quantity of wastewater, or quantity of or volume of the reaction solution what we are using, it based on which the percentage of removal efficiency and the quantity of hydrogen production varies. So these are the other photocatalysts and the concentration of sulfide used. So those are synthetic sulfide used from sodium sulfide, and these are the previous publication from our group, and we have used both industrial wastewater collected from refinery and from sewage treatment plant, and observed that maximum conversion of 50% achieved in case of using 3,250 ppm of sulfide, and in case of using 1,080 ppm, we have observed maximum conversion of 20% and maximum production. And from this, we observed that while increasing the working volume of water, the percentage of the percentage of conversion as well as the production is increasing. So this is the main finding from our group. And based on the other literatures reported, there are several types of photocatalysts used, like titanium oxide, metal sulfide, and other composite catalysts were used. And cadmium sulfate base gives maximum efficiency, but due to its photocorrosion and recombination of photogenerated electrons and holes, it should be mixed with some other photocatalyst or dopants, then it can be effectively used in order to stop the photocorrosion. Mostly zinc sulfate photocatalysts were used, and in case of core cell photocatalyst, the production or the efficiency is stable, is maximum, and we can see the core cell photocatalyst is thermally stable, and it is reactive and oxidatively it is stable, and also the thin films photocatalyst also will be effective one for large scale applications, and other carbon nanotube also gives maximum efficiency in case of it has several good properties like excellent electronic conductivity, then flexibility of modulating, and it gives maximum surface area, and it will extend the lifetime of charge carriers, etc. So in case of large scale on the stable in large scale hydrogen production, stable photocatalyst is required. So mostly from the literature, we have observed that cadmium zinc sulfide and titanium-based photocatalysts will be stable, but titanium oxide, once it mixed with some other noble metal or dopant, will be efficient. But metal ions is costlier and is not suitable for large-scale applications. In case of cerium oxide or cerium as dopant, it can be possible for large scale applications. So in our studies, we have selected these photocatalysts and we have done the photocatalytic hydrogen production and thin films. Also, we have tried and found that thin film gives maximum recovery of hydrogen when compared to powder material. Large scale, it is possible when using the thin films and other type of photocatalyst when compared to powder material, since it is not required for thin films to reuse the catalyst again and again. We can use it without any loss in case of thin films. So these are the carbon. We have done hydrogen production studies from sulfide wastewater using these kind of photocatalysts like carbon nanotube and cadmium zinc sulfate based and titanium oxide cerium based. So these are the methods how we have synthesized the carbon nanotube. So this is a tubular furnace in which it is used to synthesis the carbon nanotube, and iron oxide nanoparticles were also synthesized in our lab, and the carbon nanotube is blended with cadmium zinc sulfate coated iron oxide by co-precipitation method, and then carbon nanotube mixed with cerium doped titanium oxide also synthesized in our lab, and both gas phase and liquid phase treatment were conducted in the lab. So this is the precaution we have taken during the gas phase treatment, mask, everything. And then this is the gas phase treatment reactor. So nitrogen cylinder, hydrogen sulfide cylinder is used. And then several types of reactors were used in case of gas phase photocatalytic reactors, packed bed reactor, catalyst coated reactor, and catalyst dispersed reactor. And so these are the several parameters we have studied in case of gas phase photocatalytic process using various photocatalysts, and the effect of low rate, catalyst dosage, light intensity, and sulfide gas concentration are optimized, and the best value of these parameters were taken and studied in various types of reactors. The packed material used in the packed bed reactor is a vermiculate material. It's a novel material, and the maximum recovery of hydrogen the maximum conversion efficiency from sulfide gas is observed in case of tubular packed bed reactor when compared with fixed plate reactor, that means catalyst coated on the surface of the reactor, or simply the catalyst dispersed over the 5-channel reactor. So after the achievement of maximum efficiency in case of packed bed reactor, we went for bench scale type, and there also we have achieved 98% conversion. So then comes liquid phase hydrogen sulfide treatment. So several types of equipments were used to analyze the hydrogen quantity, and lux meter is used to measure the light intensity. And these are the several types of reactors used in case of liquid phase hydrogen recovery from hydrogen sulfide wastewater. All the reactors are having the capacity of 500 ml and made up of acrylic material. In case of inner irradiator, at the first you can see that alone was made up of borosilicate material, and the maximum hydrogen absorbed with in case of inner irradiated reactor, since the light source is inside, the maximum efficiency achieved. But that is not our motive. Like, our aim is for large scale hydrogen production, so we have just compared the other shapes of reactors and found the trapezoidal shape gives maximum production. And further we have you use that particular trapezoidal reactor for scale up in case of bench scale studies. These are the industrial sulfide wastewater collected from various industries like tannery, petroleum refinery, common tannery effluent treatment plant, and sewage treatment plant, and found the maximum concentration from petrochemical refinery. Next to that, the sewage treatment plant has maximum sulfide concentration. And while studying the conversion efficiency and the production of hydrogen, the sewage treatment plant gives maximum hydrogen production and conversion efficiency as well. So further, we have taken the STP wastewater for further studies. Also, we have recovered sulfur from similarly simultaneously. After the hydrogen production, sulfur is recovered, and it found that equal concentration of hydrogen and sulfur concentration were observed. And outdoor solar studies show that the maximum hydrogen production is in the month of April-May, since the light intensity is maximum during that period. And outdoor solar studies were conducted with the several prepared photocatalysts and found maximum efficiency for several runs, and up to 7 runs also the maximum production was observed. And the same trapezoidal type reactor was made in bench scale and study and achieved maximum hydrogen of up to 4 to 450 ml. So these are the various parameters, operating parameters studied in case of liquid phase photocatalytic hydrogen production, effect of sulfide catalyst dosage, and photocatalytic solution volume, and pH and recycling flow rate, and best values were found for maximum hydrogen production value. So you can see the initial concentration of sulfide wastewater, it's yellow in color. So after the experiment, we can see the solution, photolytic solution color is colorless, and this shows all the sulfide is converted into polysulfides, and partially to and partially it will be converted into the hydrogen will be separated, and other sulfide materials were precipitated as polysulfide materials, and this polysulfide materials we have converted into sulfur. So from this findings, from this research work, we can say that photocatalytic process will be the suitable method for recovering hydrogen and sulfur from hydrogen sulfide when compared to cross process. And also the sulfide wastewater can be utilized for recovering the hydrogen, and it will be the environmentally friendly, sustainable and cleaner photocatalytic degradation technology. And when compared to gaseous phase, liquid phase gives maximum conversion efficiency and maximum production of hydrogen. That too, gaseous phase is not advisable to work with, and recovery of hydrogen from hydrogen sulfide wastewater, it will be the suitable parent. The photocatalytic process will be the suitable parent for recovering hydrogen from hydrogen sulfide process. Thank you.
Thank you, ma'am. So that was really excellent on varied topics of hydrogen production from different reactors as well as it also stated with different pH conditions and wastewater treatment and several other methods for hydrogen production. Thank you so much, ma'am. And I have a small query. So you were saying like instead of going for a fully dispersed version, it is better if we go for thin film coated photocatalytic test. So do we have any test performed? If so, what kind of reactor is used for that?
Yes, ma'am. Actually, we have conducted the thin film studies, and it is under review. Before it is again submitted for reconsideration for publishing. And already we have studied the thin film photocatalytic process using the same reactor of same quantity of same volume. That 5 liter capacity trapezoidal reactor we have used to study the hydrogen production using thin film photocatalyst. So, and it is observed that maximum concentration of hydrogen is observed when compared to nano, when the photocatalyst is in nano form, when compared to that, the thin film photocatalyst gives maximum production.
Okay, ma'am, it is coated on some material.
Yes, it is coated in acrylic material, acrylic plate.
Okay, ma'am. So that's really nice, ma'am. So now the session is open for maximum 1 or 2 questions. If there are many more questions, you can please send to me so that I can redirect it to Preeti ma'am so she can answer you later. So any questions from the audience?
Hi, ma'am. Hello. Yes, ma'am. I have a small question that you have reported with metal halides. Could you please tell me which is better, either metal oxides or metal halides? Which is a better catalyst for generating hydrogen from H2S containing water?
Metal oxide is actually the metal oxide we have not used. Actually, sulfide, cadmium sulfide and zinc sulfide we have used, but titanium oxide mixed with cerium dope was used. But it is always better to mix with the photocatalyst. Means the metal that means the oxide materials when compared to metal dopants. So since the metal dopants are very costlier and it won't be suitable for large scale applications.
Okay, thank you.
Thank you, ma'am. Thank you so much for your excellent talk on today's renewable energy hydrogen production. So thank you so much, ma'am. Thank you.
Thank
And
you.
looking
Thank you
forward
for the
to see you at our university as well.
Sure, ma'am. Thank you, ma'am.
So now to the next speaker. So Dr. Paparao Mondi, you can share your. So now we have Dr. Paparao Mondi, who is going to give a talk on characterization of nanomaterials, which is an important aspect of once we have the material and get it characterized. So characterization and analysis becomes the biggest part of nanomaterials or advanced materials for any applications. So this talk is given by Dr. Paparao Mandi, and to summarize him, in a professional way, he is a self-motivated, independent, and innovative material scientist with hands-on experience in new product development, quality assurance, operating of TEM, SEM, EBSD, etc. These are the equipments which he is well versed with, and he has a hands-on experience. And he is also working in a metallurgical testing lab with the experience on simulations for metallurgical problems like sheet metal forming, rolling, etc. and he has core qualifications in all aspects of metallurgy, ranging from powder metallurgy, high temperature resistant coatings, finite element analysis, and managerial skills, and several others, to name a few. And he worked as assistant manager in JW Steels, Karnataka, from June 15 to 19, and later now he is working as a scientist at JNA RDDC, Ministry of Mines, Nagpur, from 2019 to now. And he did his PhD from IIT Madras, and MTech from NIT Trichy, and Masters from Andhra University. And he has got a patent, and he is editorial member of several journals, and he is also reviewer of several journals, and he has several international publications to his credit. Now I welcome Dr. Paparao Mundi to give his talk on characterization of nanomaterials. Welcome. Yes, we can hear you. Okay. Hello. Sir. Sir, Dr. Paparao, sir. Hello, sir.
Am I audible?
Yes, you are audible now.
Ha.
Yeah.
Thank you for your nice introduction. And first of all, I would like to thank the organization team of Advanced Material for Energy and Environment Applications 2020. And this is Dr. Paparao Mundi. I'm working as a scientist in Jawaharlal Nehru Aluminum Research Development and Design Center, Nagpur, which is under autonomous body under Ministry of Mines, India. Today, I would like to talk on the characterization of nanomaterials. So, the outline of my topic is a class. Hello, audible?
Yes, sir, audible, sir. Yes, sir, audible.
Application of nanomaterials and sample preparation techniques for scanning electron microscope and transmission electron microscope, imaging by SEM and TEM, and types of diffraction patterns and indexing the diffraction patterns. So, nanomaterials are the materials here which are in the range of 1 to 100 nanometers. And we have the classification of nanomaterials like zero dimensions nanomaterials, like clusters, which are the examples of TiO2, titanium oxide. And these all three dimensions are in nanoscale. And one more classification is one-dimensional nano materials, like nanofibers and nanorods and nanotubes. So, for example, as carbon nanotubes and nanofibers, which are shown in the SEM image. Okay, then two-dimensional nanomaterials like films and coatings. So, the graphene oxide layers are other nanomaterial coatings on bulk materials, and three-dimensional nanomaterials like the polycrystalline materials. So, polycrystalline metal where the grain size are in the range of 1 to 100 nanometers, and these are called nano crystals, like nanomaterials. And coming to the other, like for example, we say the gold is having three kinds of shapes. which have the nanocubes, which are in the range of 100 nanometers, and nanospheres, nanorods. And suppose we have a titanium dioxide here, which is in the cube and as well as a sphere shapes, and we have a core shells of iron oxide. So the figure E shows this one. And other thing is like AFM image of polymer wrapped carbon nanotubes on mica with Z scale as color code. And so how we can prepare this nanomaterials for SEM as well as TEM. Suppose you have a powder sample as well as you have a biological sample, and also you have a bulk material or sample. So how we should prepare a sample for the SEM as well as the TEM. So I will go one by one. Suppose you have a powder sample and you want to prepare it for SEM. So first you grind the powder and you have a specimen stub, whether it is a steel stub or it is aluminum stub, it should be a conductive medium. So on top of that, you have to paste some conducting tape or carbon tape, so which is a conductive medium. Upon that, you have to sprinkle your powder. So then you have to do the air blowing so that the excess powder will be go out. So then the material is ready for the SEM analysis. So this is how you have to do this powder analysis for SEM. And suppose you have a biological objects like a spider and an ant or some neuron or some human hair, red blood cells and all. So there are two techniques by which we can analyze the SEM by an SEM. So one is the conventional coating method. So here we have to have a cultured sample. Upon the first we need to do fixes. We have to fix the biological sample here, and then after that we have to rinse it. Then dehydration has to be done slowly. So once the dehydration has to be done, then we have to do this metal coating. So there is a critical point of drying has to be done. Otherwise, what happens is like if you are over drying, your material damage, like your sample, you will be damaging your sample. If it is under drying, then some moisture will be there, so that will give some problem in SEM analysis. So the other method is like graphene coating. You have a graphene layer, so graphene sheet. So you have to place your sample, then you just place the graphene sheet upon it, and then so then you have to give the natural drying, then it will be ready for the SEM analysis. So this is how we should do the biological objects for SEM analysis. And suppose you have a bulk metals and alloys. So first of all, how you have to do the preparation for this bulk metals and alloys? You have to polish the sample with grit like emery sheets. So starting from 120 grit size to up to 1000 or 1200 grit size, and then you have to do this diamond suspension liquid polishing with a special cloths. And once it is done, you should get a mirror surface polish. Then if you want to see some grains, so you have to etch it with a suitable etchant, or if you want to see some inclusions, as it is, you can see that. So during this SEM preparation for these bulk metals and all alloys, you also should take care of while preparing the sample, like with a bandsaw and abrasive saw or some grits. So there is called a depth of damage. So you have to keep it in mind that suppose you are applying with some pressure and using some bandsaw for FCC, suppose copper material, so the depth of damage will be 85 microns. And suppose if the grid size is 1000 grid size with silicon carbide paper, the depth of damage is 2.8. So you have to be very careful when you're looking for nano features with this depth of damage. So the depth of damage should be low as possible. So when you're preparing a sample for the TM analysis, suppose if it is a powder, first we need to crush the powder, and then then you have to keep it in the ethanol, that crushed powder or whatever it is there. Your pinch of powder you have to take and then put it in the ethanol, and then that whole ethanol powder, hello, has to be kept in the ultrasonicator. Then we have to deposit the entire thing on the carbon film, or it's a copper grid. So the copper grid generally having the carbon film with the adhesive of the formwork. Okay, so the under that this is a grid. So we can see some features here, nano features. So you can see the TEM copper grid here, and then these are the carbon blocks, and these are the nanoparticles. Okay, so this is how we have to prepare a nano powder samples for TEM analysis. And suppose you have a cross-sectional samples like a thin films. So how we have to prepare a thin film samples for TEM analysis? So first of all, you have a, suppose you have a coating sample. So this is a thin film. You have to section it like this. So this is like a half circle cylinder, and you have to just keep it this way, and there is a tube. Okay, so this is a molybdenum grid tube. So then you have to just section it with a 0.5 mm. Then again you have to just do with a dimple grinder, and then after that we have to do some ion milling. So then the electron transparency region thick will be around less than 100 nanometers. Then you will say that the sample is ready for the TEM analysis. And suppose you have a bulk metal like a sheet, or it is like some steel material. So how we have to do sample preparation for this material for the TEM analysis? Suppose you have a bulk sample, then you have to slice it with a diamond saw, low speed diamond saw, up to 0.5 mm thickness. And from that we have to reduce the thickness up to 120 micron with a grinding wheels like different various silicon carbide emery sheets. So then we have to do disc punching. So the disc size should be, the diameter should be around 3 mm diameter. So by disc punch, there is a punch. This is for metals. If the material is like a brittle material, you have to do with ultrasonic cutting. And once it is done with the 3M disc, then again you have to do this dimple grinding as well as the ion polishing, and then you have to use the electrolyte like jet polishing, twin jet polishing. So then or you have to do the ion milling, suppose if it requires. Then the electron transparent region will have around 70 nanometer to like 50 to 70 nanometer, and then you say that that material is ready for the TEM analysis. So if you have a polymer material, then ultra microtome is the one. So from bulk to this less than 100 nanometers, you can prepare with the ultra microtome. There is one equipment. So if you have a biological samples, then you have to just fix it and then dehydrate it. And this is the epoxy resin, and then resin infiltration has to be done for the just giving strength for the epoxy. Then we have to embed it, and then after that we need to section it. So once the sectioning is done, then it is ready for your like biological samples TM analysis. So you have to place this sample holder, and you can view this cross sectional C elegans, suppose for example. So when we go for this imaging, when you have these nanoparticles, so you can view them by SEM and TEM. So the SEM, suppose you see the silica nanoparticles, so those are in the range of less than 100 nanometer. So once you view this, then you need to measure each particle. Then you have to just draw a diagram, like this is a particle size distribution analysis diagram. So we can come to know that the frequency, highest frequency range of particles. So suppose this is the SEM image of the silver nanoparticles. So the 10 nanometer particles are in a highest range. So, and this is the TM analysis of these silver nanoparticles. So we can see the similar things by TEM. And you have a gold nanoparticles. So these are the image showing, and this is the grain size, like a particle size distribution map. And suppose you have so you can see that gold nanoparticles, and this is a nanoparticle where you see that five-fold symmetry is there, and these are the lattice fringes. And you can see also see with a high resolution TEM that the interlattice spacing is 2.42 angstroms. And also you can see that the twin boundary in a gold, this is a twin boundary. So this in both sides you can see the mirror image of the lattice of the atoms. So these are the uses of the SEM and as well as TEM, just to see the morphology and then shapes of the nanoparticles with SEM and TEM. And suppose you have a nanowires, one-dimensional nanomaterials. Suppose you have a silver nanowires, and this is a low magnification TEM, and you have a high resolution TEM. So you can see the core of a silver, a single silver nanowire. So you see this is a five-fold symmetry crystal and nanocrystal, where you can also see some of the twinning, twin boundaries. So by TEM, we can see the twins within the single crystal, as well as the how many folds are there in this crystal. Also, we can see that. Suppose you want to analyze a thin film imaging by TEM. So already I have discussed about how we have to prepare the thin film for thin film samples. And suppose you are seeing a cross-sectional image of the silica and ZNO interface. And this is the low magnification image of the TEM, where you can see this is a bulk material. ZNO is our thin film, so zinc oxide. So here we can see clearly that lattice fringes of these ZNO, which are in the range of 4 to 6 nanometer. And this is of course a protective layer or adhesive, so which will be connecting both the thin films together. And also you can see that, okay, this is a 4 to 6 nanometer, as well as the lattice fringes we can see at a high magnified TEM image. And this is also one of the example of silica with indium oxide interface. So this is silica and this is indium oxide, which is having the 7 to 10 nanometer layer thickness. So the TEM will be applicable for measuring your thin films thickness. Suppose you are seeing, you want to see the virus, and of course, suppose if you want to see some coronavirus here, and each coronavirus having the less than 100 nanometer, and suppose you see the schematics of coronavirus here, it has four kind of proteins here. One is a spike protein and envelope protein and nucleoside protein and membrane protein here. So here clearly we can see in the SEM that the spikes here, and this is a protruded spikes, so that is why that is called crown. coronavirus. So that is called coronavirus. So these spikes will help in the virus entry into host cell. So SEM will be used for the just diagnosing or analyzing this coronavirus, and also will be used for some of the identifying the suitable vaccines. So for finding out the suitable vaccines, this SEM will be very helpful. Suppose you have a different kind of vaccines, DNA vaccine, RNA vaccine, and other viral vector vaccine, and all the things. Suppose currently now available is a mRNA vaccine. So if this is injected to the patient and then this mRNA vaccine, and this will actually kills the spikes as well as the all proteins and then destruct the total assembly. That is how it will just kill the coronavirus. And this is a coronavirus, like this is a virus imaging by TEM. So after sectioning, as I said before, so you can view this coronavirus with like spikes. So this can be just the colored one can be kept by externally, these spikes and all. So this is you can say the size of the coronavirus now is less than 100 nanometer diameter. And suppose you see that suppose if you want to analyze the aluminum, silicon, copper, magnesium, the alloy by TEM, and you have that alloy with aging at 190 degrees centigrade for 6 hours. So you can view different particles here, different morphological particles here. Suppose you have the red indicated this discs have this L2Cu particles which have the 90 nanometer diameter, and blue arrows indicates the globular shape, and those are in the range of 50 to 100 nanometer in diameter, and the green color globules or needles have 2 to 5 nanometer in diameter. So then if you do over or suppose aging at 350 degrees centigrade for 12 hours, so then you see the particle size will be little bit in that increased. Or you can see that Al2Cu plates have 50 to 100 nanometers, and especially the arrows which shows these dark and globules of 450 nanometer diameter. Earlier it was 2 to 5 nanometer because of the high temperature aging as for long period of time. So the globular needles, the beta prime, beta double prime particles enormously increased here. And suppose you see that acicular precipitates in PK, the alloy, so you can see some HRTM here. So you can see some precipitates here at the PK condition. And also you can get some diffraction patterns here. This is the Fourier transformation diffraction pattern, and this is simulated pattern for the same alloy. And suppose you have a carbon nanotubes by TEM. So suppose your carbon nanotubes are multi-walled carbon nanotubes. So these are the 100 nanometer inner dia and 9 concentric walls and clearly inner channels. So you can see that you can count the number of walled carbon nanotubes. So these are 10 nanometer, 9 concentric walls, multi-walled carbon nanotubes. And suppose you have a single walled carbon nanotubes, you can see only one in this. So the interface between this is called the diameter of the inner diameter of the carbon nanotube. So once you get this imaging, then we have to index the diffraction patterns. So this is for TEM especially. So the types of diffraction patterns, we have a spot diffraction pattern and ring diffraction pattern, spotty ring diffraction pattern, diffused ring diffraction pattern, and textured diffraction pattern, and double diffraction pattern. Let us see one by one. Before that, suppose you have a electron beam, and this is your sample, and this is your say crystals. Okay, so oriented in different directions, and so you have these diffracted beams here, and those will falling on the objective lens, and after that these construct like a parallel. These red beams will be coming here and converging here, and then give one diffraction spot. So these parallel beams are diffracting here and then giving a diffraction spot here, and this is a diffraction plane, what we call, and the other one is this is the image plane. So where we get a image here, STM image. So comes to this diffraction patterns. So one is a spot pattern. So suppose you are your TM beam is within the crystal, will get a spot by actually as compared with the previously explained diagram. So suppose your beam is focusing or covering the 3 grains, you will get a spotty ring, so which is nearly just a ring pattern. And if it is having, like, suppose if it is covering a 50 grains or more than that, you will be seeing that a ring pattern here. Suppose in nanocrystals we should get a ring pattern, but actually that grain should be in the range of 100 within the 100 nanometer range. And other patterns are like diffused ring. Suppose you have a polymer material in your sample, or it is a amorphous material, and you will be getting a diffused ring pattern. Okay, and if your grains are, like, suppose your material is textured material, and you will be getting a textured pattern. So because of the similar orientation of the grains oriented in some similar, like one direction. So that is why you have to get a texture pattern here. And suppose you have a hydroxyapatite powder, and this is amorphous, so you will get a diffused ring pattern. Suppose you have a crystalline hydroxyapatites, because hydroxyapatite powder will have amorphous as well as a crystalline nature. So if it is in crystal nature, you will see the rings here. So suppose if it is amorphous, semi-crystalline, that means your material contains amorphous as well as a crystal. So you will also see the diffraction pattern amorphous, like, diffused ring as well as the ring pattern, diffused pattern as well as ring pattern. So also you can see some spots, which is clearly indicates that in your material some crystals are also there. So suppose, for example, this is a presence of amorphous indium oxide layer overlapping the crystalline film. So this is indium oxide thin films where you see the semi-crystalline amorphous visible. Once after getting this diffraction pattern, then how we have to measure, and how we say that this is FCC material, then this has the lattice parameter of this much. So if you know this Bragg's law, 2D sin theta equals to n lambda. Suppose your lambda much smaller, suppose at 200 kV at 0.0251 angstroms, and if E is 2.5 angstroms, then theta will be 0.288. So 2 theta, so 2D sin theta becomes 2 theta equals to sin theta equals to R by L. So R by L is the camera constant, and R is your plane length here. So this is your diffraction, like this is your diffraction spot, and this is your optical axis here. So you can derive that like RD equals to L lambda or lambda L here. So in how to index this diffraction spot, there are two methods. One is camera constant method and a ratio method. Suppose you know the camera constant, then you can go with the first method. If you do not know the camera constant, simply you get a diffraction spots. So in these two cases, how we will measure this, how we will index this diffraction spot. So you know that L lambda equals to RD. So L and lambda both are constants, and so that's why this is a constant here. And you know that R1 and D1. Suppose you take this. This is a diffraction spot, and this is a transmission spot here. So if you want to index this one, so you have to measure R1. So because there you will have one micron like reciprocal marker here. So with that you can measure this R1. So then D1 you can come to know what is a D1. That means interplanar spacing of this lattice you will come to know. So likewise you will measuring this D2 and D3. So once you are finding out D1, D2, D3, there is some database. Suppose if your material is FCC material, first of all you should know whether it is FCC or BCC and all. So if your material is FCC material and these are the D spacing values and these are the HKL values. So this is already database already given. So this is available in the books. So suppose your D1 value is 2.01 or it is closely matching with 2.01 and your material is gamma Fe, then you can simply keep this HKL value here. Okay, 111 like this. So your D2 is 1.79. You can keep the D2 here. So it is like this. So after measuring like or finding out the D1, D2, D3, you will also index these HKL values accordingly. And suppose your material is BCC material, and the same thing you have to do it. Okay, if it is HCP material, here this is already given in the database. And the second method is like suppose you got a diffraction pattern and you do not know the scale at all. So how we will index this? So for that ratio method is available. So you have to measure with a scale. You have to take a printout or you can do it in the computer. So you have to measure this R1, R2, R3. So you have to place this R2 by R1 and R2 by R3. So always keep the diagonal one upper or in the nominator side. And so R2 by R1 and R2 by R3. And so you always so A by B are like R2 by R1 and R2 by R3. Suppose you have two ratios here, you have to compare with different patterns. These patterns are also available. Suppose yours is FCC material, these patterns are also available. So you have to see that what is R2 by R1 and R2 by R3. These values are matching with these patterns or not. Suppose if these are matching, then you can just index your patterns as given in the sheet. So this is for FCC material and this BCC and HCP material. Suppose you have a complex pattern here, you have to just divide these patterns. Like suppose this pattern, you have to divide this one into pattern 1 and pattern 2. Suppose this is a one like a zone axis of 100 and this is zone axis of 111 of FCC and BCC. So you have to just divide like or subtract one on another. So this is how you have to index. So these are the some of the examples of using the SEM as well as in TEM, what are the things we can analyze and the applications of the TEM in various fields. Yeah. So thank you for giving me this opportunity. Thank you once again, and the session is open for any questions. Hello.
So thank you, Dr. Paparao. So now
Yeah. Welcome.
the session is open for questions. So any participant can ask the question.
Hello.
Hello.
Yes, sir. If it is a new material
Sir.
whose structure is unknown, how to calculate these values? Because you said if it is a FCC, there is a reference, and if it is a new structure and new material, how to find these values?
Sir, can you speak loudly? I am not able to hear you
Yes, sir.
properly.
Sir, actually, if it is a new material, how to
Yes.
find these values? Because we don't have any references.
Yeah. So if it is a new material, suppose if you are going for any TEM, first of all we need to do XRDs. Okay. So once you come like and that is a good question, and you have to design your own like this. Yeah. So suppose you know that but if it is a new material, you can find out with that lattice parameter A,
Okay, sir.
right? So once you know the lattice parameter, you will come to know the D value.
Yes, sir.
So once you know the D value, then you have to design your own patterns here, like this. So you have to design your own patterns with all these HKL Miller indices.
Yes, sir.
So that is how we have to do for the new materials.
Thank you, sir. Thank you.
Hello.
Yes.
Yes, I have a small question, sir.
Please.
While measuring a despacing value, in most of the cases we'll get some errors. How to eliminate them?
Yeah, actually the despacing value will, that error will come. So generally that is because of your stigmatism or any like instrumental like like some errors are so maximum you need to see whether your spots are in the really you are getting without any aberration, or so that you need to decide, and you so you can just suppose like which kind of material you want to use, like so what is your material?
We used to have CDS, TiO2, polycrystalline materials others.
Okay. So first of all, you need to see whether your microscope is aberration free. So suppose if it is aberration, with aberration, you will be ending up some errors. So if everything is okay, then you probably get a good pattern. And while you are measuring, whether you have to take the despacing between between the two spots, you have to just take from the center of the spot. So that is also one thing. And one more thing, that your camera constant also will be varying with increasing with different voltages and different magnification. So that also you have to be careful. There are a number of factors involving in this.
Okay, sir. Thank you.
Yes,
Thank
please.
you, Dr. Paparao, for your excellent presentation.
Yeah, welcome, ma'am. Thank you very much for giving the opportunity.
Yeah, you're welcome. And actually, I could go through some of the slides, and while some I couldn't be there, but still, I could see that there were many questions among the chat box, even through the participants also. Thank you so much for your participation and making our workshop more successful. Thank you.
You are welcome, ma'am.
So for today, I'm just ending this session. So tomorrow, I request all the participants to be there at 10 o'clock. We will start the new session tomorrow at morning 10 o'clock. Thank you so much for all of you for your kind attention and participating and asking questions. I request all some of those who haven't asked questions and participated in the discussion, kindly please participate and make this workshop more fruitful for you as well as to us. Thank you so much. So I'm ending this session for today now.